Welcome everyone, we're solving another problem today. I'm going to try to fit the solution of this problem just in one page. So I'm going to write kind of small and keep my written content low so we can fit everything in one page. Let's read the problem together. A boy throws a stone horizontally from the top of a cliff of height h toward the ocean below. The stone strikes the ocean at a distance d from the base of the cliff. In terms of h, d, and g, the gravitational constant, find the expressions for a, the time t at which the stone lands in the ocean, b, the initial speed of the stone, c, the speed of the stone immediately before it reaches the ocean, d, the direction of the stone's velocity immediately before it reaches the ocean. Let's just get going. So I'm going to draw a picture first to see what's going on here. Here is the cliff. We actually know the distance of the cliff. It is height, h. That is this distance here. There is a person up here standing, and they throw a rock, and it says they throw the rock horizontally. So what this means is the initial velocity of the rock is just in this direction, and then the rock follows some kind of path like this. You know, you guys have thrown rocks before, so you can kind of imagine what this looks like. And then it hits the shore below, which is water, which I'm going to draw like this. And we also know that it hits over here a distance d from the shore. So this creates a nice xy coordinate system. If we set up 0 over here, so this is 0, 0, if we go this way on the x-axis, then this position over here, d, is pretty important. And if we go vertically here on the y-axis, this position over here is the height h. So this point over here, we can call it 0 on the x, h on the y. That's pretty cool. And this point over here, we can call it d on the x and 0 on the y. So these 2 points are created from the system if we set up the coordinate system like this. You could set it up in other ways if you want, but this is kind of clean. I'm going to use this. If you set up another coordinate system, just kind of be consistent. We should end up with the final answer in the end. Now that I've drawn a picture of what this looks like, I also kind of want to model the motion of this rock, because if we model the motion, we can figure out the speed of the stone before and after. We can find out the time it takes for the stone to land in the ocean. We can find all these things, but we have to break stuff up. And how I like breaking stuff up is doing stuff in the x direction and in the y direction. So I'm going to split this up like that. In the x direction, the stone is thrown completely horizontally. So this is model of particle under constant velocity, right? V in the x direction initially times time plus x initial. This is the equation for the position as a function of time for a particle under constant velocity. This is the constant velocity. So I'm kind of stating this and adding some information to the problem. So right over here, we could even draw this. I could say v initially in the x direction, or v in the x direction initially. It doesn't really matter what you call it, just be consistent, is equal to, well, we don't know. We're just going to leave it like that. But keep in mind, this problem says solve it in terms of h, d, and g. So we're not really going to have any other numbers in our problem. We're not going to find the answer to this in terms of a number. We're going to find it in terms of this thing, and g, which is the acceleration due to gravity, 9.8 meters per second squared. But we also don't need this number here because they're asking us to solve it in this term. So we could just leave g, and hopefully this thing here, if we need it, we could just build it up from this, and g. We will see. Anyway, this is the equation the stone follows in the x direction. Let's also write down the y direction. And in the y direction, this thing is being accelerated by gravity. So it's particle under constant acceleration. Constant acceleration. The equation for constant acceleration, the position as a function of time, and notice now we're talking about the y, so I'm just using the letter y. Before we were talking about x, so I used the letter x, and here I use the initial x. Here we have kind of the same thing at the start, the initial position, and the initial velocity in the y direction times time, but we also have this acceleration term. Nice. So now we have two equations. This equation is what the rock will do in the y direction, and this equation is where the rock will be in the x direction, right? And we can connect them and see what happens. Let's pull out some information from the problem. We got 2 points of interest. This point right here, I said before, was 0 on the x, h on the y. And this happens at t equals 0 seconds. Then the next point of interest is over here. This happens at t equals t final, which we actually don't know what it is. But we do know that this is at a position d on the x-axis and 0 on the y-axis. This is from when I set up everything in the coordinate system. So using these two pieces of information, these are points, right? This is a y point, this is an x point, this is a y point, this is an x point. Here we have a y equation as a function of time and an x equation as a function of time. And we also have 2 points in time that we could split up the problem into, the initial point and the final point. So let's just plug in the initial point because we know the initial point. We're just going to call it t equals 0. Let's plug this in over here. So x at t equals 0 is equal to the initial, we don't know what that is, times 0 plus the initial position of the rock is right here, and this is at x equals 0. So xi equals 0 in our problem. So this equation simplifies as x at t equals 0, or t initial, is equal to 0. That just means the problem says that the rock starts at x equals 0, which is right here. Awesome. We just saw that with this equation, so that's pretty cool. Let's do the same thing with y. Y at t equals 0. Well, this y initial is not 0 because it starts at a height h, right? So here is the y coordinate at t equals 0. So we could say this is h plus, what is the velocity initially in the y direction? It is actually 0 because here it says the rock is thrown horizontally. That means all of its velocity is pointing in the x direction. In the y direction, the vy initially is equal to 0. So because of that, we can put 0 here. And then whatever t is, it's going to be 0. So we can get rid of that whole thing there. Basically, this whole thing equals 0. So we could simplify the equation a bit. Now we have 1/2, we have g, and then we have t squared. And keep in mind that we're plugging in t equals 0. So right here, if I plug 0, then this whole thing gets canceled out. So we could just erase this. And what this tells us is that the y coordinate of the rock at 0 seconds is at h, which makes sense. This is given to us from the problem. So I'm just checking these equations, these two equations, which we said should obey this problem. And I plugged in a point over here, which is given to us. And I saw that initially the x coordinate is 0. This is true. And initially the y coordinate is h. This is true. Nice. So what can we do here? Well, we have another moment of interest, which we could do the same thing. So I'm going to use the same equations here, except now I'm going to make another division. So originally, I had all of this work done, and this was done at t equals 0. Maybe that was a little bit too large. I'm trying to save space here. I'm going to go like this. Boom. Now we can do at t equals t final. We don't know what t final is. Remember, t final is something that they're asking us for in part A, but I'm just setting up the problem. So let's do the same thing. Remember where we started. In the x position, our object, the rock, follows this kinematic equation. And in the y direction, it follows this kinematic equation. We can replace stuff here, like we know y initial is h. We know x initial is 0. We don't know the velocities. We know this velocity is equal to 0. And we know that a can be replaced with g. So let's do that simplification. Let's keep everything split up into x and y. Maybe I'm not going to be able to do this on one page. So here I'm doing x at t final is equal to, well, it's 0, then it's v x initial times t final. All right, what can this tell us? Well, I kind of want to see what position on the x-axis the particle is in at the t final. And if we look at this, we actually are given this x position. We are given this d. So I'm going to plug this d over here into this. And I could just do that by doing equals d over here. Now, if you guys want, we can isolate for t final since that's what we're looking for. And how we do that is just d over Vx initial. So this is an interesting equation, which I'm going to box in this green color. But it doesn't give us the answer because remember, they asked us to find things in terms of h, d, and g. Here, we have it in terms of d and this Vxi. And remember, the Vxi was just me introducing it. So I'm not allowed using this in my solution. I'm going to lose some marks. So what can we do here? Well, I'm not sure. We're just going to go through with the same thing for the y equation. You know, I don't know what to do with this equation, but it's maybe important. Like I can't simplify it any further. I can't get any more value out of it. Can't solve any of the problems with it. So I'm just going to keep it here and then do the same thing that I did here, but with the y equation and see if we get some value out of that. So here is y at t final. We know that y initially is h, and we know its initial velocity is 0. So this is 0, and this here is h. And then here we have plus 1/2 g. I replace acceleration with acceleration due to gravity. And here we have t final squared. And also, I want to know the y value at t final. Well, if you look at this, at t initial, y is h, and then it falls down. And eventually, at t final, y is 0. It is on the 0 point on the y-axis. You guys see this? So that gives me a piece of information from the problem, which allows me to put 0. So basically, what is the y-coordinate at t final? It is 0. That's purely from how we define the problem. But you got to know how to put it together. So now we're kind of at the same stage as we were with the x equation. I had an equation over here, and I could just isolate for t final. Here I have a new equation, and I can isolate for t final and see what we get. So I have t final squared is equal to, you have a minus h here over g, and there's a 2. So you guys see what I did? I just moved this h on this side, so I get a minus h, and then I divide by g on both sides, so it gets canceled here, moves here, and then I multiply by 2, and that isolates for the t squared here. If I want to isolate for it further, I can square root both sides, and I will get this over here, which is the next equation that I'm going to kind of outline in green. So this is an answer because what we have is h and g and t final, and here is the number 2 and a square root. So that solves the problem A, which is the time t at which the stone lands in the ocean in terms of h, g, and is there d in here? No, it's just h and g. But there's a problem. Have you guys tried to take square root of a negative number? It doesn't work. Maybe once you get to more advanced math, you can see they define this as I. This is not what we're going to do today. When we see a minus sign under a square root, in our case, this is a problem because time is not an imaginary number. Time is a real number, so you cannot have this minus sign. This minus sign is a telltale sign that something is wrong. What is wrong? Well, the thing that's wrong is gravity here should be negative g. You guys may have seen this in some problems, like gravity is pulling the rock down, so we direct it with a minus sign. It is pulling in the negative x or negative y direction, and that's why the rock falls down. But you may be curious why, how, and how can I confirm this in the future? Check out this equation over here. This is the equation for y as a function of t, and you have all these symbols and stuff in it. This value is given to you. It is h. It doesn't matter if it's 10 meters or 20 meters or 100 meters. It's given to us here. 1/2, we know what this is, and t is a variable in this function. I can plug in t equals 1 second, t equals 5 seconds, t equals 1 hour, and this is a function of time, so this will give me the y coordinate as a function of time. G is also known, 9.8 meters per second squared on Earth. But if you don't put a minus sign in here, this value is positive, and this value is always going to be positive. If this g has a plus in front of it, this value is positive. So as we increase time, as we plug in 0 seconds, 1 second, 100 seconds, 1 hour, 1 day, this thing will always grow and grow and grow, and it'll always be positive. So a positive number plus a positive number means the y-coordinate will always be more and more positive. So what that looks like is the rock starts here, then it just goes up this way. This is not physical. It doesn't make sense. That's why you have to put a negative sign here, because at the initial time, t equals 0, the height is h. And then every following second, you subtract this amount from this h. So that's why you need the negative sign here for this equation to work. If this was a negative quantity and each second you subtract from this height h, that models this problem nicely, because at 0 seconds, this h is where the particle starts. Every subsequent second, it loses more and more of its height because it's falling. Make sense? So always ask yourself, if you see an equation with g, try to plug in g equals positive 9.8, g equals negative 9.8, and see what happens, and ask yourself if this makes sense. You should be chilling. But as a rule of thumb, if you're quick, short on time, always use g equals negative 9.8 meters per second squared. You should be chilling. So going back to this, if this was a negative thing, then I can move this on this side, and this will become positive, and this will become positive. So this thing is positive. Or if that didn't make sense to you, originally we had a negative sign here, but if we also add negative g, there's going to be two negatives, and these guys cancel, and the whole thing is positive. Knowing that, we should fix this equation too and put a minus sign here, and now everything should be correct for future analysis. And also, you don't have a negative under the square root sign. So this is the answer for part A. Boom. Clean. Hope that was good. Hope that wasn't too much time. Let's check out part B. The initial speed of the stone. How do we find this? This is the initial speed. This is Vxi. We determined this. We just stated, like, you could call this any letter. You could call it h. You can, no, actually don't use h because there's h here. But I just called it v in the x direction initially. You guys might have a different way of, labeling variables. Check it out though. This equation is circled and it's green, and it has Vxi in it. And it also has t final and d. We need d. We need to have the final answer in terms of d and g and h. T final is also found over here. So I could equate this t final with this t final. Everything here is in units that we like, or not units, but symbols. We have an h here, we have a g here, we have a d here, and we can isolate for our value of v. So this is for part B. I'm just going to equate those two equations. So on one side we have d over Vxi. On the other side we have square root of 2h over g. Now we can isolate for v. Vxi is equal to d over square root of 2h over g. And that is the answer for part B. You guys see it took a long time to set up the problem, but now we're kind of swimming. We got two answers in like the span of 10 seconds-ish. Nice. And these are all the terms that we are allowed to use, d, h, and g, right? We got d, we got h, we got g. Nice. So that solves this problem here. By the way, it says initial speed. Here I labeled it with a v as if it's the velocity. I do this because here, I don't know if I'm going to have to break up into vectors and stuff, and velocity is a vector. So I work with the velocity first. That's also what you put in this equation. And then the final thing is, if you want to convert from velocity to speed, you just take the magnitude of the velocity vector. In this case, since the magnitude of the velocity vector is fully pointing in Vxi, if I find just Vxi, I'm chilling. I don't need to find Viy. I also found out Viy was 0. So this is the full magnitude of the vector. Nice. Shall we do part C? We will. But I just want to mention to you guys, if you're solving something in symbols like this, and you see these symbols, you have Vxi, you're like, am I on the right track? You could do a unit check, and this is very nice. So let's do that super quickly. I'm going to do it in this pink color. I'm going to write all the units of these things over here and just copy the same equation, right? So I have d. D is in meters, right? You can go back to the picture here. We have d. It is the distance from the cliff to where the rock falls. So that is in meters. On the bottom, I have square root. Inside the square root, I have 2. 2 is unitless, so it doesn't change anything with our unit analysis. h is in meters. I'm putting everything in square brackets just to be really obvious that these are units. And then g is in units of meters per second squared. Okay. So on the top we have meters. On the bottom we have the square root. And here we have meters times seconds squared per meter. So I flip this bottom fraction, multiply by this. I hope this is okay with you guys. Check out how to do operations with fractions, how to divide fractions, how to multiply fractions. Brush up on that, you should be chilling. These 2 meters cancel. Let me use this green actually. These 2 meters cancel, and the only thing that's left is seconds squared, but seconds squared is being square rooted, so it gets canceled here too after canceling the square root. So all the units left on the bottom are seconds, and the meters on top stays unchanged. So we have meters per second. This is the final unit of everything inside here, and it is the same unit for velocity. So checking the units like this just makes you very certain that you are kind of on the right track. And it's good to do if you ever have an extra minute to double check your work. All right, let's check what we have for the next problem. We did A, we did B. C is the speed of the stone immediately before it reaches the ocean. Damn. Okay, so we found the speed over here, and we found how long it took to get over here. So what can we do? Could we just... Well, this is the position equation, and this is the position equation. Can we find velocity somehow from here? So I had to think about this initially, but what we need for the full speed at the bottom is, well, I drew the rock falling completely down, but it's more likely that it's kind of falling at an angle like this, right? So its velocity vector would be going at some angle like this, right? Let's say this is the water over here. It's going to do some angle here in the negative water because it falls in the water like this. This angle is going to be important for part D, which says find the direction. But you can also break this up. So here we have the v final in the y direction, and over here, right here, we have the v final in the x direction. We need to find both of these values, and then we can use Pythagorean's theorem and some SOHCAHTOA, and we will be able to find the total length of this final vector here, and we'll be able to find the angle. So that's going to solve these last two things. But you got to think about the motion of the problem. So it's thrown originally horizontally, and in the x direction this thing is going in constant velocity. Constant velocity means the velocity is not changing. So initially the velocity is this, and finally the velocity will be that. Basically this guy throws it with this initial velocity, and over here it'll still be going with this initial velocity in the x direction. So the x component is already found. It is exactly this, but we have to find the y component. How do we do this? In the y direction, we have constant acceleration, but this equation is not going to help us. This equation is for position. You got to think about which equations you learn about, and in the y direction, there is one that has the velocity in it, but I can't remember what it is, so I'm straight up going to search it up. All right, guys, this is the equation here, very important. In an exam, you're probably going to have an equation sheet, but in this scenario, I just searched up velocity, kinematic equation, particle under constant acceleration, or check the back of the book. This is one of the important equations, and in this case, I think this is a good equation to have. So check out what we have here. We got the final velocity squared. This is what we're looking for, the final velocity in the y direction. So we're going to apply this equation just in the y direction. That means it's maybe kind of useful to put a y here and a y here. We actually know what the initial velocity in the y direction is. It is 0. So this whole thing gets crossed out. We know what 2 is. We know that acceleration is g. Is it positive g or is it negative g? We're going to see that. And then what is this delta x? This delta x is the change in position of the particle. But in this case, they put a delta x because they're just using x. In our scenario, we are interested in the y direction. So it's displacement in the y. Remember, you're applying one equation in one direction and another equation in another direction. So you want to keep your units or your components split up. In this case, I got this y here, this y here, this y here, and acceleration in the y direction is literally equal to g. So we're Boolean. Let's try to plug in some values here. So we have v final squared, which we're looking for. We have 0 over here. The initial velocity is 0, so I'm just going to delete that to save some room. We got 2, we got g, and here we have delta y. So it's y final minus y initial. Let's check our picture. Here is y final. So y final is 0 minus y initial is over here, right? It starts at h. So delta y is equal to 0 minus h, which is equal to minus h. Boom. So here we have a minus h. Now take a look at this equation. We were curious if g is plus or minus. If we have a square over here and we want to square root this to cancel this to isolate v final, I take a square root on this side. I can't do it with a minus sign here. So we're going to have minus g over here because this minus will cancel with this minus, and then I'm allowed to take a square root of a positive quantity. That's just something I'm spotting. So if we have minus g and minus h, I'm just going to erase this and simplify it like that. And also take a square root on both sides. So this is the v final and the y. It was very quick. I kind of didn't write a lot of the stuff, but I am trying to solve the problem on one piece of paper. So basically what I did was just use this equation, plug everything I know in, work through some minus signs, and then we get this. And this is very important. So I'm going to circle this in green as well. Boom. Nice. So now we have this and this. I'm going to draw a very tiny picture right here. So the rock falls like that, right? We found over here, this is the Vx final, and we found this over here. This is the Vy final, and this is the V final. So what we can do is do a squared plus b squared equals c squared. We find c squared, we're going to find the magnitude of the final velocity, and that is going to answer question number C, part C. The speed of the stone immediately before it reaches the ocean. Speed meaning magnitude of the vector. But we needed the components to find that magnitude, so keep that in mind. And D, we're going to do this all in one step. Find the direction of the stone's velocity immediately before it reaches the ocean. So this direction, what they're asking us to find is this angle right here. I'm going to call this angle theta. And how we can do this is tangent. So I can use SOHCAHTOA. I'm just going to write SOHCAHTOA over here. SOHCAHTOA. Boom. So we can use TOA because the opposite side of this angle of this triangle, the opposite side of this is over here, and this is the same as this, and that is Vy. And we have Vy. Vy is right here. And adjacent is the adjacent side of this triangle to this angle. So the adjacent side is right here, and this is Vx final. So if I do y over x, tangent inverse, then I can find theta. So actually I'm going to write that equation over here because we're going to do it all together. Theta is equal to tangent inverse of, it is the opposite, which is v final y, over the adjacent, which is v final x. Awesome. And let's get cracking. I'm going to keep stuff here in pink and do v final is equal to square root of d squared over 2h times g plus 2gh. Okay, so I did some simplifying here. A squared plus b squared, I basically take this and square it, so that's where I get the d squared from, right? Because I square this whole thing. The square on the bottom removes this, and then I move this g up here, because if this was a and this was b, then I just multiply by this fraction flipped, so this g goes to the top, and this 2h stays on the bottom. Nice, and we can check the units here if we want to as well. The second thing is b squared. This thing, if you just square it, the square root gets removed, so it's 2gh. And this is actually the full answer. I'm going to put this in green. It looks a little bit weird, but like I said, this is a symbolic problem, so If you want to double check, just plug in some units, do some unit analysis to see if this gives you a final velocity, and you should be chilling. So this is part C. Let's do part D over here. Theta is equal to tangent inverse of v final y, which is square root 2gh over v final x, which is d, and I'm going to do the same fraction flipping, put this here, 2hg. And you can simplify some stuff here as well. Like what I see is here there's a square h. So square root of h times square root of h is just h. You can pull that out. Here we have square root of g, so you can cancel those as well. So at the top you just have 2h, I think, over d. So I think you can simplify that there. Maybe you can simplify some stuff here, I'm not sure. But this is the final answer. I'm going to circle this as well in green. So here's the one page solution to this. Let me know if you guys like the solution method. And while you guys are looking at this, I'm just going to pull up the solutions to this. To see if I did everything correctly. So part A is t final is equal to square root 2h over g. That looks good, amazing. Part B is v in the x direction initially is equal to, they did some flipping around, but it's the same answer as what we got. Beautiful. C is the magnitude, and it looks like we got the same thing. Amazing. And D is the angle. It looks like we have the same thing, except they simplified like how I showed you. So I hope this problem was pretty interesting. Let me know if you want to see any other ones, and if you have some time, or if you're curious, or if you need to practice for an exam, just open up the Survey and Jawed book, go to the back of the book and back of the chapter. Go to the back of the chapter and pull up any problem that is interesting and just try it out. Well, I tried this problem out with no solutions. I kind of just argued my way through it. Try this out as well, and if you ever get stuck, take a little break, and if you're still stuck after the break, search up a solution online. You should be chilling. Keep practicing. Let me know if you need some help, and good luck. Peace.